So in this video, you're going to learn how to pick a network protocol for your IoT project. And my guest to present that information to you is Frédéric Desbiens. Frédéric is the program manager for IoT and edge computing at the Eclipse Foundation. Welcome to Expert Talks here on Industry 4.0 TV, which is a series of sessions where we bring in subject matter experts to present on various IoT topics. My name is Kudzai Mandi Teresa, and I'm your host here on Industry 4.0 TV, where I regularly publish industrial IoT content. So if you're new to this channel, please do subscribe and click on the notification bell so that you don't miss any of our content. Now, over to you, Frédéric.
Thank you very much, Kudzai. Thank you for having me, and thank you everyone for watching. So let me share my screen. Okay, so the goal of this presentation is really to help you out if you are in the IoT game already or just starting and you're not sure exactly what protocol to pick. So the goal there is to give you a few guidelines to help you pick out the right protocol, and at the same time to give you information about some of the options that are right there in the market right now. So the agenda there is really 4 simple points. First, I will establish why you need to choose a protocol, because not everyone is convinced that you need to pick an option. So I will explain you why it's so important to pick one. And when I say one, it can be several, depending on how large your project is and the kind of stuff you're trying to do. But essentially, you need to make choices. Then we'll cover a number of established players in the market, so protocols that have been around for, in some cases, more than 20 years, provide a bit of details about that and implementations that you can leverage. And then we'll focus on what I call the emerging challengers. So at the Eclipse Foundation, we have a number of projects that are trying to push the envelope a bit in the protocol space, and we'll take the time to have a look at those. They are lesser known, but well worth your consideration. And finally, I will provide a few guidelines about how you can choose exactly the right option or set of options for your particular project. Okay, so why do you need exactly to choose? You know, on the next slide, I will show you a few quotes that I heard from people in the industry. You know, people in some cases that were even experienced IoT developers, and those people seem to imply that, you know, you don't need to pick one of those specialized IoT protocols. You just do with whatever, and that's not really the case. I don't necessarily agree, but let's see what they have to say and why they are wrong. So the first one, why do you need to choose? Use this censored, you know, I removed the product name there, with it multi-protocol support. Yeah, there are plenty of gateways, plenty of products, platforms that support multiple protocols. But in the end, between a specific sensor or constrained device and that gateway, you will need to run one, you will need to pick one. So the fact that there are very flexible platforms that support multiple protocols doesn't alleviate for you the need to look at your requirements and pick the option that makes sense for your specific use case. Then in the middle, REST is simple, it's supported everywhere, I don't need anything else. And certainly REST is nice. The problem with REST is that it, you know, runs by definition over HTTP. And HTTP is not something that you want to deploy on a constrained network with frequent outages where you need to save on bandwidth and that kind of scenario. You don't want to do that. You know, REST works well on the public internet, on a wired network, and the same with HTTP, but really, yes, REST is simple, but you are losing on many, many interesting features if you just pick that, you know, and use that as your magic hammer, you know, to solve every problem that you may have. So don't do that, please. And finally, some people will tell you that plain TCP/IP is good enough. And certainly this is a lower level option. It works, it's widely supported. But the problem with that, you know, you are working on an IoT or even edge computing project. You want to deliver value to a customer. You're not delivering value to a customer when you are manually parsing, you know, all of those payloads that you extract from packets and assemble all of that yourself by hand. You know, this is something you don't want to do, because in that case, you're not focusing on the business problem. right? You're trying to reinvent the wheel, working with a lower level, at a lower level layer. And sometimes maybe you won't have a choice to do that, but in many, many cases, you have options. So please pick a higher level protocol and run with that. So the reasons why picking the right IoT protocol for you for the job, picking the right tool for the job are so important. There are mainly three big reasons there. First, when you pick a protocol, it impacts many things, many characteristics that the solution you are building will have. The performance or throughput that you will get, the battery life, your own productivity, the level of security that you can deploy. And rolling out your own custom security is never a good option. So you have to pick a protocol option that really will help you, build a secure solution without once again requiring you from reinventing the wheel. Then, plain HTTP is missing many, many features. There's no notion of quality of service, of reliable delivery, or anything like that in HTTP. And obviously, those things are really, really important when you are building IoT solutions. You are making sensor readings, or you are sending commands to a device in the field. Then obviously, you need those commands, you need those, to be delivered, you need that data to be delivered. And obviously in some use cases, maybe missing a reading is not that bad, but ultimately, if you want to build a robust solution, then you need quality of service, reliable delivery, and many other things. And HTTP is lacking in all of those departments. And finally, in the end, using a lower level option like plain TCP, or even something, manipulating network packets directly, other kind of stuff, this will slow you down. And your goal as an IoT developer is really to bring value to your customer and bring value as soon as possible. And that means working with a higher level option is the right choice. Okay. Now that we established this, let's have a look at a number of protocols that have been in the market for a while and that are good options, I think, for an IoT project. And we are talking here about COAP, DDS, MQTT, and lightweight M2M. And maybe some of you will say, hey, there's an option missing. We don't see OPC UA in there. Well, OPC UA would be, a topic large enough for a series of presentations, given the level of complexity that there is in the ecosystem. So I'm putting it aside for this time. It's certainly an option in many scenarios, but then you need to figure out, will you use the pub sub transport, or will you use the client server transport? Will you use this or that? So I wanted to keep things simple, and that's why OPC UA is not the focus today. But please remember, this is certainly an option you can leverage in the field as well. Okay, so COAP is the first protocol we are looking at. So COAP stands for the Constrained Application Protocol. So already you see the design, or the intent in the name really is to focus on constrained devices. And COAP lives at the Internet and Engineering Task Force, IEFT. So it's documented in a series of RFC. So I put on the slide the number of the main RFC for COAP, but there are many authors that define additional features, as the protocol group. Anyway, you start with RFC 7252, and you go down from there. There are hyperlinks all over the place. Really, the goal of COAP is really to run with minimal overhead on the network. Okay, it can run on any device that will support UDP or a UDP equivalent. And if you're not a networking expert, right, UDP is part of the Internet suite of protocols, but it doesn't provide the ordered delivery that you will find in TCP/IP. So UDP uses IP as the lower level, but it provides what we call datagram delivery, which is simply you're sending, messages or packets right there, but there's no ordering guarantee, there's no delivery guarantee or anything like that. So UDP is lighter weight because it doesn't provide all of those added features that you find in TCP. And this is why, it's a good option for very constrained devices. Now, COAP by design okay, has been engineered in a way that you can use it to communicate between devices on the same constrained network. Okay, so over, let's say, a Zigbee connection or something like that in the field, LoRaWAN or that kind of stuff is certainly doable as well. So low power, lossy networks, okay, by design, this will work well, but it can work over the internet as well. Okay, and that's a strength. Since COAP has been built and is overseen by the same people that manage TCP/IP and HTTP and all of those standard internet protocols, then it's got a level of interoperability with that. And that means you can route COAP traffic over the public internet and that kind of stuff. And this means you can use COAP between devices on different constrained networks that are joined by the public internet. And that's really one of the great strengths of that particular protocol. Now, in terms of architecture, COAP is really very close to HTTP. It uses the request response model that HTTP uses, and really it uses the same verbs. So get, post, put, delete, it works in the same way. So if you like REST, you will like COAP because it works exactly in the same way. But it's much lighter weight. It doesn't have all of those headers and all of that. And so you will save on bandwidth. COAP also relies on the concept of URIs, response codes, MIME types, and can even use IP multicast for device discovery or even communications. Obviously, in that case, in the case of multicast, you need to make sure that your network provider or your network admin, if you own the network, will configure the network to support that. By default, many network admins don't like multicast. So, if you try it and it doesn't work, assume it's your network blocking you and not necessarily COAP, which is at fault. So what kind of features COAP provides? Well, first, it's completely asynchronous, and that's in the spirit of HTTP as well in that department. It provides very low overhead, and the payloads are very simple to parse. And by default, every payload in COAP will be encoded in binary, and the stack will take, take charge of the serialization and deserialization. But by putting all of those payloads in binary, you make them smaller and easier to transmit, and overall, you're consuming less bandwidth. So once again, we see the focus on constrained devices here. COAP supports URI and content type, as we mentioned, and the nice thing, since it's so similar to HTTP, you can proxy COAP traffic and even use caching servers on the network in order to make the infrastructure more reliable. So overall, very close to HTTP. And if you're tempted by REST, please have a look at COAP. Now, this is the protocol stack for COAP. And obviously, an interesting option if you are on constrained devices, you want to use Bluetooth, you have here the 802.15.4 support, okay, which essentially means that you can run IP version 6 through 6LoWPAN in order to have COAP traffic over a Bluetooth connection, for example. So by default, Bluetooth doesn't support IP traffic, but with those set of standards, you can achieve that. So if you have, let's say, a little constrained device with a Bluetooth connection and then some edge node, a gateway with Bluetooth support, you can establish connections in that way to route the COAP traffic. We see here in the middle, there's UDP and something called DTLS. And essentially, to secure COAP traffic, you will not use plain TLS, you will use DTLS. And DTLS is the lighter weight version of TLS, using the same kind of certificates and all of that to get encrypted traffic. So obviously, if you're deploying a real world application, you should run UDP plus DTLS in the middle. And then the various layers of the COAP protocol are on the top. So the base support is for messages, and then there's the request response model on the top of that, and your application will leverage that in order to send and receive messages. Okay, so if you are getting started with COAP, a good implementation to work with would be Eclipse Californium. So Eclipse Californium is a full client and server implementation of COAP written in Java. And, it supports many of the additional RFCs, that bring additional features to COAP that have been developed over time. So there is this notion, for example, of observe notify. By default, since COAP is request response. You send a request, let's say, to /home/temperature to get the reading of the temperature sensor, and you get a response. But what if you want to be notified that there's been a change in that temperature reading and do something about it? Then this is where the observe notify pattern is useful. And so essentially you declare an observer on a specific resource, and on the server side, when the value for that resource changes, you get a notification. So instead of polling all the time, which is the IT equivalent of, are we there yet? Are we there yet from your kids? You don't want to do that. So instead of polling all the time, you get a notification when the value changes, and this makes your solution more scalable. And at the same time, you save on bandwidth, you save on battery life. There's also in COAP, in another RFC, the notion of blockwise transfers. So essentially, if you have a large payload, you can chunk it and then transmit it in several messages instead of just one. Once again, this makes the whole thing more resilient, because if one message fails to transmit, you just retransmit that one instead of resending the whole thing. Californium supports the latest DTLS standard, and it's got also experimental implementation of COAP over TCP. So by default, traditionally, COAP was running over UDP only, but now you can run it over TCP if you want it. Let's say you have a wired network and you want to leverage full TCP there, then you could do it. And there's the notion as well of something called OS Core, object security for constrained RESTful environments, that provides a more granular security model for COAP. I won't expand on this, but let's say that you can secure specific attributes in objects and not just the full objects themselves. Californium also support, it provides a cross proxy to bridge COAP and HTTP traffic in both directions, a scalable web resource framework. And if you like the OSGI component model, then it provides a wrapper for that, so you can integrate it into any OSGI compliant server. By the way, if you work with constrained devices, you will certainly use real-time operating systems. And so the Zephyr RTOS from the Linux Foundation, for example, has native support for COAP as well, and it integrates and interoperates very well with Californium on the server side, so you can leverage that together without any problem. Okay, enough with COAP. Let's move on to another protocol, the Data Distribution Service, or DDS. DDS is really different from COAP. COAP was request response, and in the case of DDS, we are, in a publish and subscribe setting. But the thing is, maybe you heard already about MQTT or other publish and subscribe protocols, and typically those publish and subscribe protocols would rely on a broker somewhere, right? Well, in the case of DDS, it's publish and subscribe, but without any broker. In fact, one of the design tenets for DDS is that there is no single point of failure in the infrastructure. Okay, this essentially means that any node can be a publisher, a subscriber, or both at any time. And essentially that you build those meshes or even cliques of nodes, okay? And the traffic will be routed, between all of those nodes in the infrastructure. Okay, so this is very useful, for example, in robotics, aerospace, in all of those settings where you have many potential nodes that need to transmit data to each other in real time and coordinate together. So if you have a swarm of drones and you're trying to direct them in order to do an air show or something like that, with lights and lasers, then DDS would be a very good solution for that, because essentially out of the box, it provides you automatic discovery, it provides you many, many things. And this means, once a node joins the network, it will be able to find with the authors and then start publishing and subscribing to whatever it feels is important. So DDS is a specification owned by the DDS Foundation, which is a component of the Object Management Group. So OMG is the home for UML and other interesting things, but in their case, they started this little specific foundation to be the steward of the DDS protocol. So what are the features of DDS? First, it provides spatial and temporal decoupling between applications. Essentially, if you have an application that's sending, publishing messages to DDS infrastructure, this is fire and forget. You won't get an acknowledgement or anything like that. You're just sending messages. And if you're subscribed to something, you will eventually receive messages about a specific topic. But the point there is really that those applications, when you send a message over DDS, you don't know who is listening or who's subscribing. You don't care. You just publish your messages, and if someone is interested, then they will get the message eventually. Okay, it's completely decentralized, so there's no central broker or anything like that. So you can start with just 2 nodes, and then it builds from there. But what's really interesting about DDS is that it provides a full set of quality of service policies. And essentially, this enables you to specify when the data is available, where it is available in various ways. So this is much more granular than say, hey, I want reliable delivery or not. No, there are, if I remember, was 17 distinct quality of service policies. And it's the combination of those that sometimes will mean that some nodes will be matched together for publishing and or subscribing. And finally, the built-in dynamic discovery aspect of DDS is really important. That's one of the strengths there. So essentially, if I were to demonstrate DDS here, I could start, a publisher node, I could start a subscriber node, and they would find automatically one another if they are on the same network, and without any configuration needed. Okay, obviously there's a cost to that in the sense that there is network traffic required for that auto discovery mechanism, right? So nodes are advertising themselves on the network in order for authors to find them. Okay, so you have to balance battery life versus the niceties of automatic discovery. But in many scenarios where DDS makes sense, this is not necessarily a concern. Okay, so what's the stack for DDS? So essentially, to run DDS, you can use either TCP or UDP. But this is implementation specific. Not every DDS implementation will support TCP, so you have to be careful there. The way DDS is built is that there are, in fact, 2 sub-protocols, so to speak, that are part of the wider DDS standard. The first one is DDSI RTPS. So that's the real-time publish and subscribe component of it. And this is the transport layer. So essentially, you could run just that particular layer of the protocol, although nobody does that in reality. But it is in a separate specification, and it is decoupled from the higher layers in DDS. And then you have DCPS, okay, which is really the layer where the publish and subscribe model is implemented. And really there, what is interesting in DDS is that the payloads are strongly typed. So essentially, when you declare a publication, you will at the same time declare the object type for whatever data you are publishing. which means, you know, the subscribers will get that only if they require the same type on the other end. So if you want a good implementation of DDS, there's the Eclipse Cyclone DDS project that you can leverage. It's a pure C implementation of the protocol, but there are language bindings in other languages, including Python. So, you know, if you want to work with a higher level language than C, then you know, you still have the Python binding to work with. It runs with minimal runtime dependencies and is very compact. You know, it can fit as small as 512 Ks of memory. So, you know, unless your device is very, very small, you should be able to run it. It supports multiple platforms, so Mac OS, Linux, Windows for development, and a series of real-time OSs on the constrained device side. And what's nice about Cyclone DDS is that it's seen adoption in robotics. So in the last edition of the ROS2, so the robot operating system, you know, Cyclone DDS is the default middleware in that specific version of ROS2. So certainly, if you work into robotics, Cyclone DDS is without a doubt an option that you should have a look at. Going on now with lightweight M2M, another option. So lightweight M2M is a protocol really focused on lightweight, low power devices and really focused on sensor networks and machine-to-machine environments, okay? So essentially, until the latest version of the COAP specific, not the COAP specification, but the lightweight M2M specification, lightweight M2M required COAP behind the scenes to run. Now you can run over MQTT and other protocols in the latest version of the spec, but the COAP option as a transport is certainly the most mature that you have. So many things in lightweight M2M are very close to what COAP provides, but what makes lightweight M2M different is that it defines an extensible resource and data model. What this means is essentially that you have predefined types for many types of sensor data, okay, that you can leverage, that are part of what is managed by OMA SpecWorks, so the home of the lightweight M2M specification. Okay, so they have this whole not a dictionary, but this repository of resource definition. Okay, that define, let's say, for temperature, I have a temperature sensor and the reading is this. Okay, so you can reuse those existing types in your application, which makes them interoperable much more easily. Because when you think about it, COAP is request response, and I talked about the fact that you send those requests and you have those payloads, but COAP doesn't say anything about the payloads. So essentially, what lightweight M2M does is really to bring those standard sets of payloads and resources that you can leverage. And the model is defined in an extensible way. So if you build solutions that you put into the market, you can propose, you know, to OMA SpecWorks additions to the repository of resources. So this is something you can leverage, and many players in the market have been doing just that. You know, they bring sensors or very complex machines to the market, and they provide the lightweight M2M data model in the repository for others to leverage. So over COAP, lightweight M2M brings a lot of added value. For example, it comes with this notion of bootstrapping. Essentially, you know, if you are a device maker, you can ship your lightweight M2M devices to your customers, and then your customers in their networking environment will have this bootstrap server. So they plug the device, and the device will search for local bootstrap server. They will get some information, and from there will auto-configure for the customer environment. So this is really a powerful mechanism, really interesting. Lightweight M2M also provide features to support device configuration and firmware updates that are built into the protocol. So that's really, really strong there. It provides fault management, configuration, device configuration, control, reporting. So you see, we are at a higher level than what plain COAP does. We're not talking about plain messages or anything like that there. We are talking about value-added features that are really targeted at constrained devices. So the lightweight M2M protocol stack is really a bit larger than the COAP one, because essentially, although COAP has been for a long time, the default transport option, when you look at what's underneath, it supported a wider array of transport options. So for example, CIoT, LoRaWAN, even SMS. So, the text messages you get on your phone, you can run COAP over that. So this brings an added level of flexibility, and this is fully documented in the COAP specifications. Now, not the COAP specification, the lightweight M2M specification, sorry. Now, not every lightweight M2M implementation supports all of those options. So please have a look at the documentation, before making choices and starting drawing your architecture. Okay, that's really important. So at the Eclipse Foundation, we've got 2 projects that are targeted at lightweight M2M. First, there is Eclipse Leshan, and Leshan is a library for implementing clients and servers. It's written in Java, okay? And essentially, you can use that to build your own or to integrate lightweight M2M into existing server-side or even client-side solutions. So it's very simple. There are very few dependencies. It's not using a third-party framework, anything like that. It comes with a web UI, which is very useful for discovery and testing. So even if you don't work with Leshan to build your solution, you may want to use the test server. It comes bundled with just for interoperability and things like that. And it's based on Eclipse Californium as a dependency. So we are drinking our own champagne, so to speak, there. And so 2 Eclipse projects are working there together. Then there is the Wakama project. Wakama is a C client implementation, okay, that you can leverage. It's pure C, so it's very portable, and it will run on Linux or even any constrained environment that will support the POSIX APIs. And last but not least in our list of established protocols is lightweight M2M. So lightweight M2M, sorry, MQTT. So MQTT is the most mature of the 4 options I discussed. It's been around since 1999. And at the time, really it was a proprietary technology of IBM, but IBM contributed at some point those the specification and design for MQTT to the OASIS consortium. So essentially, now it's owned by OASIS. It's a fully open standard. By default, MQTT runs over TCP, but there is a specific version of MQTT that's called MQTT SN, and the SN there stands for Sensor Network that runs over UDP. So it's fairly flexible in terms of transports as well. And initially, MQTT was targeted at SCADA use cases, okay? If you're not familiar with SCADA, essentially that's a supervisory systems that go into factory or into industrial settings. So systems that monitor industrial infrastructure and send commands to specific devices on the network and things like that. Okay, so I'm simplifying it a bit there, but essentially this is what SCADA is all about. So essentially, the people who invented MQTT were trying to monitor and control oil pipelines. And they were trying to do that over satellite, but existing protocols didn't work well into such an environment. So essentially, they built MQTT, and the rest is history. Now, MQTT is a publish and subscribe protocol, which means that essentially, when you are sending messages, they are not meant to be stored in a durable fashion. Okay, so you send a message, it's consumed somewhere, and there at the other end you will store the data in the database. But don't use, the broker, which is at the center of the MQTT architecture, as a kind of database. Oh, I publish data there and I leave it there. No, that's not the right way to use the protocol. So MQTT brings really well-defined levels of quality of service, and you can pick whatever makes the most sense for your use case. So you can have at most once delivery, at least once, or exactly once delivery. And obviously, as you go from at most to at least to exactly, there is a bigger overhead, obviously, on the infrastructure. So at most, or quality of service 0 is certainly the most scalable one, and exactly once, which guarantees that a message will be received only a single time at the other end, is the most onerous one, because there are so many exchanges between the publisher and subscriber in order to assure that the message is delivered only once. But this may be very useful in very specific settings, so you have the option to leverage that. MQTT also has this notion of persistent sessions, which means if a client disconnects, and when it reconnects, all of the existing subscriptions will be reestablished without having you to write code in order to do that. So this is really useful. It's got the notion of retained messages. So essentially, a retained message is you publish, let's say, temperature data for a sensor. The data will be kept as the last known good value on that particular topic or on that particular value, which means that if there was a client that was offline, when it will reconnect and establish a subscription, it will get that message because it's the last good value for that particular topic. There's also the notion of a last will and testament, which means essentially when you have a publisher, you can, when you establish a connection, say, hey, if I disconnect, please send this particular message to this particular place. Okay, and this enables you very easily to know if devices are online or offline, because if you receive a last will and testament message, this means the network connection broke with your publisher, for example. And then MQTT sessions can be kept alive over TCP, so it takes care of that. So this ensures that you don't need to reestablish sessions all over the time because of those keep alive mechanisms that are built into the protocol. So this is the MQTT protocol stack. So we see the standard version of MQTT that runs over TCP, MQTT SN that runs over UDP. There are small differences between the two versions, but essentially from a functional standpoint, MQTT and MQTT SN work in the same way. Now, if you want to work with MQTT, we have three options for you at the Eclipse Foundation. First, there is Eclipse PAHO, which is a collection of MQTT clients in several languages, Java, C, C++, Python, Go, Rust, etc. So you have, many choices there. It brings a very extensive feature set. Automatic reconnect, offline buffering, message persistence. This is really strong. You can, if you want, even use WebSockets instead of plain HTTP. If you are big on WebSockets, then PAHO supports that particular transport for MQTT connections as well. So PAHO is a set of clients, and since MQTT is built on this concept of a central broker, then we have a number of brokers at the Eclipse Foundation. One option is Eclipse Mosquito, which is a very lightweight broker written in C, which is included in the repositories for most Linux distributions already. Very a popular option. It's really optimized for size and speed. Okay, so it's a very nimble option. And then there is Eclipse Amlan. So Amlan is a scalable broker, okay, which has been open sourced by IBM. It was part, At IBM, it was called IBM Watson IoT Platform Message Gateway Broker, which is a mouthful. Anyway, so it was the MQTT broker and the IBM Watson IoT platform. It's been open sourced at the Eclipse Foundation. And compared to Mosquito, this is an MQTT broker which a larger footprint, but it will integrate with GMS and custom protocols on the enterprise side. It brings high availability and clustering as well, which is something that's not necessarily available in open source Mosquito. So an interesting option if you're trying to deploy an enterprise MQTT backend. Okay, so up to now, we discussed protocol options that live outside the Eclipse Foundation that are managed by various open organizations like OMG or Oasis. And now what we are focusing on are two protocols, Sparkplug and Zenoh, that completely live at the Eclipse Foundation. The first one is Sparkplug. So we just covered MQTT. Okay, one of the great strengths of MQTT is that it's very flexible. Since the specification doesn't say anything about the payloads, you can put any type of data in an MQTT message. There are obviously limits. You cannot put more than 256 megabytes of data at the same time and that kind of stuff. But, you know, in practical terms, you can do, nearly everything with your MQTT payload. But the bad thing about MQTT is that the specification doesn't say anything about the payload. So let's say you have this robot and then you have software, both support MQTT, but you know, the robot will try to publish information somewhere. The software doesn't know what this somewhere is, and out of the box, they cannot interoperate. Okay, so you have in that specific scenario to spend some time to massage the payloads or configure the environment so that publishers and subscribers will, you know, point to the same place. And anyway, you don't want to do that. Okay, and many other people didn't want to do that. So this is why Sparkplug was invented, you know, to solve the lack of interoperability in MQTT-based industrial IoT solutions. So to solve that lack of interoperability, Sparkplug brings three things to the table. First, a set of standard but extensible payloads. Okay, so when you have MQTT plus Sparkplug, you know what the format of the payload is, and it's that payload format is built in a way where you can declare your own custom metrics and things like that inside of the messages, but in a format that every Sparkplug compatible device or piece of software will be able to decode right away. Then it defines a standard set of topic structures. Okay, a topic in MQTT is the place where you publish something or where you subscribe from. Okay, so essentially Sparkplug defines what the topic structure is in advance, so you know exactly what kind of data you are getting and where it will be. Okay, out of the box. And it also, in the case of Sparkplug, supports stateful session management, which is something you cannot find in MQTT. And this is really useful in real-time systems because in that case, you have those stateful sessions. So if a device is disconnected, then once it reconnects, the existing subscriptions and publications will come back online. So this is the high-level architecture for Sparkplug. We see the MQTT broker at the center, and really the intent there in Sparkplug is that you have those edge of network nodes, okay, that run Sparkplug that are driving sensors or devices in the field, okay? And then on the other end, you have your traditional infrastructure like your historian database, your analytics, and etc. that supports the protocol. And Sparkplug identifies a role for SCADA, supervisory control systems in the infrastructure as well. So essentially in a Sparkplug solution, you will have this notion of a host application, which is the SCADA system. You have this notion of the edge of network node that is receiving data from the field or sending commands to field devices. And then you have this set on the left of Sparkplug enabled infrastructure like the historian database, the analytics system, and all of those things are defined in the Sparkplug specification, and there are features that are defined for each of those types of nodes. Sparkplug is an open specification at the Eclipse Foundation, which means that anyone can implement it without any constraints, without any royalties or anything like that. So you just download the latest version of the PDF and you can start implementing it. Okay. We provide the specification document, which is developed on GitHub. You see the URL on the slide, and a technology compatibility kit as well to verify conformance of your implementation if you wish so. And then on the other end, we have the Eclipse Tahoe project, which is an open source compatible implementation of Sparkplug. Once again, Tahoe has implementations in several languages, Java, C, JavaScript, and Python. And you can use it to jumpstart your Sparkplug efforts if you decide to do so. So some people in the market are doing just that. Some others have built their Sparkplug implementations from the ground up. But in any case, everything for those two projects, the Sparkplug specification and Eclipse Tahoe is developed in the open on GitHub, and you are welcome, obviously, to suggest new ideas and participate. And last but not least is the Zenoh protocol. So we've seen several pub/sub options already in this presentation. Zenoh is a bit of a different beast in the sense that, yes, it is a lightweight publish and subscribe protocol, but it merges, the strengths of MQTT and the strengths of DDS together. DDS is great because it doesn't have a single point of failure, but there is no central broker, and it's very difficult to route DDS traffic over the public internet. Then in the case of MQTT, there is a single point of failure, which is always the broker, so it's more fragile. So what if you can have both at the same time, essentially? Okay, some level of central node that will aggregate traffic locally and maybe communicate with each other over the public internet, but at the same time, the capacity to have meshes or cliques in the local environment. And this is what Zenoh is doing. But Zenoh is much more than just publish and subscribe. Essentially, it supports what we call store and query. So there is this notion in Zenoh of geographically distributed storage. So essentially, I told you that the MQTT broker is not a persistent database. You shouldn't send messages to the broker and leave them there forever. And in the case of Zenoh, you can have databases that are part of the infrastructure, and you can run queries over the infrastructure in order to get historical results from those databases, for example. So really, Zenoh unifies data in motion, data in use, data at rest, and even computations, because you can declare computations as something in infrastructure that you can query over the Zenoh protocol as well. And Zenoh from the ground up has been optimized for low latency and high throughput. So this is what a typical Zenoh deployment would look like in the real world. So we see in orange, we have peer nodes that are connected together in a mesh on the left, in a clique on the right. And, essentially, those are nodes that can publish or subscribe or both. There is even this notion of a client node in white, where essentially, the clients use a lighter weight version of the protocol, but they cannot be parts of meshes, but they can connect to a peer node in the local environment or a router node. And a router node in Zenoh is a bit like this MQTT broker in the sense that it will aggregate local data, and it will help, routing the traffic in the infrastructure to the right set of destinations. Okay, and I have a full presentation on Zenoh, so maybe at some point I'm coming back to talk about that. But the point here is that with this combination of client, peer, and router nodes, Zenoh enables you to build infrastructure that makes sense for your use case. And this means that you can have those peer nodes with automatic discovery, like in DDS, let's say for a swarm of robots, And then in the middle, router nodes that will bridge the various factories maybe that you have with those robots inside. Okay, and you can bridge them over the public internet. So essentially, Zenoh is overcoming the limitations that were in DDS, and at the same time, it brings all of the flexibility of automated discovery in the local environment. So this is the Zenoh protocol stack. In the case of Zenoh, what's interesting is that you have all of the usual suspects, TCP, UDP, but you can run Zenoh over QUIC as well, which is a protocol from Google with many interesting advanced features that you can leverage. And in the case of Zenoh, you can even run it as a shared memory implementation over Unix sockets, or even a layer 2 or 3 protocol, which means essentially you won't have TCP or UDP in the middle. You will run straight Zenoh on very, very constrained devices. So all of those options are possible. And this is one of the strengths of Zenoh as well, the wide variety of transports that it offers compared to other options in the market. All right, very briefly now, we covered lots of protocols, but sometimes what you need is IoT infrastructure. So something, well, to leverage those protocols in the server environment. And so at the Eclipse Foundation, we've got what we call a gateway and devices stack in Eclipse Cura and Capua. So Cura is a multi-protocol gateway implementation written in Java. It runs on the top of Linux, and you can use it to build gateways that will support COAP, MQTT, and other protocols. And then Capua is the IoT cloud that goes with that. So it can manage the gateways, it provides device management, it provides data management and all of that. So it, you know, together, they are built together, and they are at the core of commercial products by Eurotech and other Eclipse members. So one stack to have a look at. And then if you are interested in digital twins or in remote command and control, then we have what I call the digital twins and connectivity stack. The main contributors here is Bosch, where you have the Ditto project for digital twin, Eclipse Ono for device connectivity, and Ono supports COAP, MQTT, lightweight M2M, other protocols like that. So you can have platform agnostic remote service interfaces to connect a large number of devices. And Eclipse Hugbit is a software framework that you can use to deploy software updates to your devices in the field. So all of those things are built by our Eclipse IoT community. So those are the current members. We see our leader members in Bosch, Eurotech, and Red Hat. Our innovator member in IVMQ, and the rest of the gang is there. And as you can see, there are large names there. There are smaller startups and everything in between. So everyone is certainly welcome to join. Now, the big question, how do I choose? I threw lots of options your way in this presentation. So how will you, in the end, pick the right option for you? And I think, you know, there's a number of rule of thumbs to think about. The first one, your use case. Are you controlling data or collecting data or controlling devices, or both? Okay, and some of the options that we've seen, like MQTT, are very strong to collect data. You know, the publish and subscribe model in MQTT or even in Zenoh, that's certainly a good fit for that kind of use case. On the other hand, if you are receiving lots of commands, or if you need to coordinate with other nodes in real time, maybe something like DDS or even Zenoh is a better choice, because then essentially you have this notion of a local mesh or clique, and then the protocol, you know, solves lots of problems for you. So thinking about the use case and what exactly you're trying to achieve is certainly key there. Then there are the constraints, okay? When you think about IoT, you think about constrained devices, but constrained device for you is not necessarily the same as constrained device for me, in the sense that maybe in your case, okay, you have those very low power boards, but they are running over power over Ethernet, so you don't have to think about battery. You have a wired network, so you don't have to think too much about bandwidth. Okay, that's one thing. But you are deploying maybe those constrained devices on white mills in the middle of nowhere, or oil wells, or whatever. And then in this case, you are operating over battery power in a very remote environment with very limited bandwidth and bandwidth that is expensive. So thinking about the specific constraints of your project is really important, because some of the protocols that I told you about are, well, most of them are lightweight, but some of them are even lighter weight than others, okay? And really testing, before deploying is a good idea there, because you don't want to have any surprises. And then finally, there's the support. Okay, you have hardware you want to work with, or you are maybe looking for a hardware platform, but does the software that you have in mind work with that specific hardware? The specific operating system that you are thinking about. For example, the Zephyr RTOS comes with built-in support for lightweight M2M, COAP, and MQTT. Okay, that's great. What if I do DDS then? Okay, does my DDS implementation works there? I don't know. Anyway, so you have really some time to to work with the software constraints or hardware constraints that you are not the decider for. Okay, and this means in turn that this will shape the set of options you have in picking a specific protocol. And obviously, there's the whole question of sensors and devices that may be supported. Devices with built-in protocol support are a great accelerator, but obviously you need to find those with the specific version of the protocol that you want to work with at the same time. So all of those are important considerations in choosing a protocol. And now my call to action. Well, essentially, this is, in this case, please have a look at our projects and eventually use them, start contributing to them, and join us at the foundation. So in any case, thank you so much for watching this. And if you have any questions, then I'm more than happy to get them over Twitter, or you can find me on LinkedIn, and we have community meetings. Anyway, I'm all over the place over the internet, and I will certainly keep an eye on the comments on this particular recording as well, so that if anything comes up, I will try to come up with answers.
Okay, thank you so much for putting together such a fantastic presentation for us, Frédéric. I really appreciate you coming onto the show to share your valuable insights. Maybe just one question, very briefly. A good number of audience members here on this channel are industrial developers and engineers. How would you compare these protocols with regards to their application in industrial facilities in particular? Maybe very briefly.
Yeah, at this point in time, I think MQTT has got a sizable lead in those types of environments for a few reasons. First, it's been there first, right? Since 1999, the other options arrived a bit later than that. Then it's really the relative simplicity of MQTT that makes it a very good fit for those environments, in the sense that, it strikes a good balance between being lightweight on the bandwidth versus being flexible enough with, delivery guarantees and all of that, deliver the kind of features that IoT developers were looking for in order to build robust industrial IoT solutions. But at the same time, what has been limiting as a factor for MQTT has been this lack of interoperability. So right now, what we see is strong momentum for MQTT plus Sparkplug as a solution to emerge. And in fact, Sparkplug existed even before it was contributed to the Eclipse Foundation. So it's not like it's a brand new option with no one making devices and software stacks for it. There are commercial products and open source implementations for it already in the market. But really what we feel right now, and we've seen that in our market research at the foundation in our annual developer survey, is that there is strong momentum for MQTT, and now Sparkplug is getting on the top of that because it provides this interoperability between devices and software stacks.
Okay, thank you so much. So now it's over to you in the audience. If you've got any questions about today's session, you can leave them in the comment section below, and we'll make sure to get every question answered. And you could also reach out to Frédéric on the contact details that is provided on the screen on Twitter. LinkedIn, and all over the internet, as you said. So thank you for joining us today, and thank you, Frédéric, for coming through to the show.
Thank you, Kudzai. It's been a privilege, and looking forward to the next time.